Okay, this lecture is about representing networks. So I have a quick question. How many you had graph theory? One.
Raise your hand fully, guys. So
Yeah. Everybody had graph theory, right? So what is the topic you learned in your course?
Representing graphs by, let's say, basic data structures, some algorithms related to graphs. We also we study graphs in both data structures and algorithms and discrete mathematics. So,
Okay.
Something like planar graphs and partial orders.
Okay, that's fine. And do you remember the notations of graph? Some theorems, some types of graphs. What kind of graphs you remember?
Directed graphs and directed graphs.
Okay, fine. Okay, then you already familiar with the today's lecture. So it will be more than an interaction than. Do you know how this disciplinary graph theory started? Do you know about this problem? What is the problem? Can you state it?
When we start at a bridge and return.
Just speak loudly. Yeah.
So this is basically an Euler cycle problem where
Yes.
we have to start at a vertex and visit each edge exactly once and come back to it, if it is possible or not.
Right. So it's called Königsberg's bridge problem. So it's a problem related to the topology of the city. Do you remember the name of the city? It's called Königsberg. So earlier it was a part of Germany. Now it belongs to Russia. And this river, Plzeň. So it has 7 bridges. What are those bridges? Small A, B, C, D, E, F. And this river divided the whole city into 5 parts. And this capital A, right? So this capital A, B, C, D. Okay. So now the question was that what is the problem? Can you walk through all this land? But what is the criteria? Restriction is here that we have to cross all these bridges once. Okay. So then Euler solved this problem and he said that this kind of path does not exist. Okay. So then he introduced these 2 theorems. Okay. Later this kind of paths are called Eulian paths. So we'll talk about later. Okay. So before that we have to know some notations. To understand this theorem, we have to know some notations of some graph theory. So this is how the discipline graph theory started. So this is the starting theorems of graph theory, right? So as I said, so the notation for graph, how we represent a graph? So we need 2 components. What are those? Nodes and edges. Okay. So here we have an example. The reds are, we can say it's the nodes, these are, right? And the link between these nodes, we can say the link or edges, right? So for a network or graph system, we need these 2 components. Okay. Okay, before that, this is actually mathematically how we define a networks. But in the real life, can we think about some real networks or real graph? Like that Königsberg's bridge problem. Can you think about? Can you give me some example?
You can think of the internet as a graph connecting web pages.
Yeah, internet is a, yeah, right. And so give simple example. Speak loudly.
Google Maps.
Google Maps, correct. So can you interpret it? What is the node and?
Nodes are the places and edges are the path.
Right. Anything else? Anything else you can talk about? So I have a few examples here. This is a more kind of economic example, like trade example, free trade networks, where we can consider nodes are as a countries and links are what? It's an agreement of free trade. So if 2 countries have some agreement That means they can trade without any traffic. If there is no agreement, they might have some, they can do some trading, but they have to pay some fees as a traffic, like that. Okay, I will have a more example here. So it's a Jackson-Ulinsky 1996, it was described as a connection model. So after this lecture, I have a more 4 lectures. So I'll talk about this paper. It's a strategic network formation, how a network is formed, stability versus efficiency. So I'll start from this paper, Jackson and Ulinsky. So in this paper, Jackson and Ulinsky talk about this connection model. What is the connection model? Here the nodes are, what are the nodes? We can talk about, there are some human beings and edges are their friends. That means they are sharing some their, what you can say? Yeah, some common interest or anything, right? So here is another example. They also talked about co-author model. So co-author model is what? So as a Professor Amit Nanavati said that in the end of this school, maybe we can have work together in some problem, right? If you have any problem, we can have some collaboration. So similarly, the collaboration is a kind of network. So where the authors, the collaborators are, we can consider as a nodes, and they are sharing some knowledge that may be interpreted as a links, right? Okay. Okay, then if we go back to this Konigsberg-Bridge problem, if we interpret it in a node as a graph, then how we can interpret it as in a graph?
The parts of the cities are nodes and
Cities are nodes and
bridges are the
bridges are their links. Okay. So then, so here I have more example. Is it visible, right? It's little bit, the fonts are very small. So first, internet, the nodes and links are what? How you are going to interpret it? Most of your background is computer science, right? So you know more about me, more about than me. So about internet. Just speaks. Just try to interpret it. What is the internet?
web pages are the nodes and the hyperlinks can be thought of as links.
Okay. 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 So similarly, mobile phone calls. When you call somebody, so from you call someone, right? Then someone going to pick it. So it's a some kind of you are going to talk about something. So it's an information sharing. So that link you can consider as a link. So then email, you email someone. That's also a network, right? That's again I said science collaboration. That is the co-author model. Citation network, I don't know you have know about it or not. Maybe we'll talk about later. Okay, these are some examples. Okay. So you can think about more about some real life example of networks. Can you think about more? Let's just try to find out some more example. Okay. So that's your homework. So then, directed and undirected graph. What is the undirected and directed graph? Just tell me. Just give me example if you don't know that exact definition. Just give me some example. So when we are talking about this example, can you think about what is the direction and undirected graph? Directed.
Under the graph, if one node is linked to two other nodes, you can go to both the nodes. Irrespective of, you can go to both the nodes, but in directed graph, you can only go to the direction which arrow is pointing.
Right, there is some direction how the link is forming from one node to another node, right? So, okay, we talked about, so we talked about some examples like emails, networks, lot of examples in the real life examples. Can you give me some example of directed and undirected graph?
One-way roads.
What?
One-way roads.
One-way road? Okay, yeah, one-way road, correct. Instagram and LinkedIn. Okay, so Instagram is a?
Like the following.
Directed, right. Then Twitter. Twitter is also directed. What about Facebook?
LinkedIn is undirected.
LinkedIn is undirected. Okay. Okay. What about Facebook? Undirected, right? And we said the email network. It's directed or undirected?
Directed.
Directed. Yeah. Okay. Okay. Then let's talk about isolated and empty graph. Do you have any idea about what is an empty graph and isolated graph? Notes?
Those who don't have any edges.
Right. Say. So empty graph means we have only nodes. So they don't like this. So there are some nodes. So they don't have any links among them. Right. And these nodes are called isolated node. So what about simple and multi-graph? So simple graph means there is only directed or undirected links. Only one link between two nodes. But if there are links like this, these are so parallel links between two nodes, then we can say it's a multi-graph. And say there is a one loop. There is a one self link for that node. So this kind of graphs are called multi-graph. Can you think about one real life example of a multi-graph? Just speak loudly.
Road networks.
Huh?
Road networks. There might be
Road networks, correct. How we can define a multi-graph there? Multi-nodes.
two ways
Two.
in two cities or two places.
Yes, correct. Or we can talk about like that, think about like this, there are two points there. So there is some highway also and overbridge also, right? What about loop? This is called loop, right? So this is a self link, it's called loop. So can you think about a loop? Any real life example of a loop?
A circular park or a jogging track.
Jogging track.
Like you start at a point or a race course.
Okay. Anything else? Like that's not clear.
In citation network, if we upload our own paper,
Okay, correct. Right, correct. Yeah. Citation network, right? Right. Or say co-author model. So a person, a collaborator who has a lot of project, but in a one project he is working alone. We can talk about this as a loop, right? Okay, do you know what is a degree then?
Number of edges.
Number of edges, correct, yeah. And in case of directed? In degree and out degree. What is the in degree and out degree? Incoming, yeah, correct, and out degree? Going out, right. So, okay, let's talk about some real life example then, say in citation network. Can you think about in degree and out degree?
So like if I cite some, for example, if the relation is that if a person A cites person B's work, then there is an edge from A to B. Then if I cite somebody's work, then that consists of out degree. And if somebody cites my work, then that counts as an in degree.
Right. So, what about the email? What is the email network?
If I send out emails, then that is an out degree.
Send your inbox and outbox or sent box, then you can consider as your in degree and out degree. So which one is your in degree and which one is your out degree? In inbox, right? And your sent box is your out degree. Correct. Okay, star graph. Do you know about star graph? So let's talk about some type of graph. So first is the star graph. So star graph, there is a one central network, right? Say for S3, this is the one central network and it has a one link, and the another they don't have connection. They only have connection via this node. Okay. For S4, this is the central network right? And another, sir, I have a link only with that sentinel nodes. Similarly, this is S5 and S6, right? So in a star network, there is exactly one sentinel node and others will have a connection with that sentinel node only, right? So can you give me an example of star network?
Let's say there is a common a website hosts a major server, and the clients which provide request to the server can be thought of as the peripheral nodes.
Okay, okay. Anything else? Celebrities and influencer. Okay, good. Anything else you can think about? Wi-Fi routers, right? Okay. Okay, complete graph. So every node has a link to everyone, right? So do you, so total numbers of, if there are n numbers of nodes, n is any integer, positive integers. So now total number of link will be nc2, right? N into n minus 1 by 2. So these are the total numbers of links. So now give me some example of complete graph, some real life example of complete graph.
It's like a very tightly knit friend group where everybody is a friend of all the other people.
Yeah, we can think about that, or anything like, if some example. You want to say?
Family, you can talk about like everybody is connected to everyone.
Family is more kind of a friendship network, right? Okay. Anything else?
Maybe a LAN network,
LAN network, how?
which all the computers are connected to each other. Maybe there is an admin computer which controls other computer through LAN connection.
Okay, all other computers also connected to each other? Okay. Okay. Okay, let's talk about then subgraph. Do you know what is subgraph? There are two kinds of subgraph. One is called spanning subgraph and another is called induced subgraph. So what is the difference between them? What's the difference between them? Any idea? So if let's take an example, it's a simple example. So there are 5 nodes. There are some, right? This is a one graph Z or network Z. So can you give me a one induced subgraph and spanning subgraph here?
You can just, let's say for example, take any two nodes with an edge between them, and that is an induced subgraph.
Okay, let me just level it, right? 1 to 3, 4, 5. So now give me a one spanning. What you said, that we can consider 2 nodes. Which node?
4 and 5 with the edge 4, 5.
4, 5. Okay. So this is, you want to say this is a
Induced subgraph.
induce.
On the vertices 4 and 5.
Ah, yeah, correct. Induce. And can you give me a one spanning?
We keep all the nodes and one.
Yeah, we keep all the nodes. We have, for spanning, what you have to do, you have to consider all nodes, but say 1, 2, 4, 3, 5, right? And then,
Take any edge.
yeah, there could be any edges, right? So not the whole graph. So this is a one, so G prime, this is a one induced graph. So there might be some isolated node also, right? And in case of induced subgraph, what is the difference between spanning?
In induced subgraph, you can delete the vertices, but in spanning, you can only delete the edges.
Sorry, can you speak again?
In induced subgraphs, you can delete only the vertices,
Induced vertices, okay.
and in spanning, you can only delete the edges.
Okay, correct. So induced subgraph means if you have to consider say some nodes, set of nodes is what? 1, 2, 3, 4, 5, And let's consider one subset of n. Give me one subset of n. S. Just give me one S.
1, 3, 5.
1, 3, 5. So the notation for induced graph, we usually use this notation. What is this mean? It's actually all the link we are going to consider that is restricted to this subset S, right? So here we have that induced subgraph. It will be like there is a one link between 1 and 3, right? Is there any link between 1 and 5? No. And 3 and 5? No. Only 1 and 3 will be there. So this is a one induced subgraph. Okay? Okay, regular graph means if the nodes has equal number of edges. Right? Say there are 4 nodes and each node has equal number of edges. And we call it as a k-regular if each node has that k number of links. So it is a 2 regular graph. And a complete graph is always a k n minus 1 regular graph. And circle, what is the circle? I am saying this circle, this is also a circle, right? So in case of there are 5 nodes, this is another circle and is always a 2 regular graph. Okay, so let's talk about dense graph. So in a dense graph is what? It's a complete graph. It's a kind of dense graph. So in a dense graph we have a lot of nodes. Lot of edges. Right? So here, there are 2 kind of networks, sparse and dense. In a sparse we have a less number of edges, but in a dense we have a maximum number of edges. So but there is no specific definition that how many nodes we can, how many edges we can consider as a sparse or dense. Okay, bipartite. Do you remember the definition of bipartite? Right? So we have a partition of the vertices. So and among these set U and V, they have only connection. So but in U there is no mutual connection among U and the nodes which are in V. So can you think about some real life example here?
Let's say, for example, if in a college the placement season is going on one side we have students and on one side we have companies, and there is an edge if one company recruits one student.
Right. Anybody else? Can you think about a bipartite graph?
In a ward, attacks are only from one partition to the other partition, not within the partition.
What?
In a ward, you can
What?
a war, like a battle.
Okay, what? Okay.
So you can think of the army personnel as the vertices, and an edge between an army personnel to another army personnel as a bullet fired or a missile fired from one to the
Okay, okay. Anything else? In a collaboration network also we can think about, right? If collaboration, say there are some collaborators are there and there are some project, right? So this is a project A and B, these are the team, they are working on this project, right? So some are working, say, both together in this 1 and 2 team working in this project A, say 2 and 3 working in the project B, right? So this can be interpreted as a bipartite graph, okay? So tripartite graph also similarly, we have a partition where the We can divide it all. We can divided that nodes into a subset. So where we can have link, this kind of link, but there is no link among the nodes which are in U and this set and this set, like that. So we have a T kind of nodes like from U to I or I to F or this kind of like that. Okay. Okay. Then let's talk about the connection in networks. So what is a path or walk? Do you know what is a path? Walk? This is just a sequence of edges from one point to one edges to another edges, right? So here for this network Z, from this point to this, we have some sequence of edges. You know what is the shortest path? How we define a shortest path? So somewhere I have mentioned about the shortest path. Okay. I think somewhere else I have mentioned about the shortest path. Geodesics or something. Have you studied about centrality to define the closeness centrality? No, sorry, between the centrality we use that shortest path. And what is the shortest path? Minimum.
Sequence to.
Yes, right. So from this point nodes to this nodes, what is the shortest path? Do you think this is the shortest path?
No,
No, then what is the shortest path?
there's a direct edge.
Direct edge, because there is a direct edge and this we call the shortest path, right? Okay, here I have described geodesic path, that is the shortest path. Okay. So in case of directed network, how we define a path?
Same thing, but we have to have a constraint that for each node.
We have to follow the direction, right? We have to follow the direction. In case of ion array, we don't need to follow the direction, but in case of we have to follow. For A to B, this is a one path. Say for B to A, we have to follow the direction. That means B to C, C to A. That's a one path from B to A, right? And cycle means what? It's a path, but the starting nodes and ending nodes should be same. Okay. So now let's talk about, this is some kind of nodes. It's a graph with some cycle. So this is a one cycle, right? This is another cycle, this is another cycle, this is a whole is another cycle, right? So tree, it's totally all nodes are connected somehow, but there is no cycle. And forest means collection of trees. Yeah. Now let's talk about Eulian and Hamilton. What is the difference between them?
Hamilton and Path, we need to visit each one node once.
Yeah, and Eulian we have to consider all
Edges.
edges
Exactly.
exactly once, and in Hamiltonian all the nodes we have to consider exactly once, right? So here this is a Eulerian part and this is a one Hamiltonian part. Okay, so now I have a one question for you. So in a complete graph, say Kn, n is a positive integer. It's a complete graph with n nodes. So can you find what is the necessary and sufficient condition that it will have a Eulerian or both Hamiltonian? Let's take an example.
Like for an Eulerian part, we present n has to be odd. The degree will be even. All nodes will have even degree, so then there will be an Eulerian circuit, and I think all complete graphs will have a Hamiltonian.
Okay, so first say Eulerian. The necessary and sufficient condition should be when complete graph will be a Eulerian and should be odd. Okay, and For Hamiltonian, I guess. So let me have a look.
Hamiltonian, I think there will always exist a Hamiltonian path.
Just a minute, okay? Just a minute. Yeah, for Hamiltonian, n could be anything, right? Okay, in case of bipartite, so do you remember what is the Eulian criteria for Eulian path and Hamiltonian path?
Like for Eulerian path, if let's say all nodes have even degree, then an Eulerian path will exist. But for Hamiltonian path, it is as such a very
No, I'm asking about that for the question 3.
okay.
So like this is for a complete graph, right? If you have a Eulerian, then both are even, right? N and M both should be even. Okay. And for Hamiltonian, okay, do one thing. We don't remember the theorems, right? But we can verify it and we can generalize it. Let's look at one bipartite graph. Say 2 and 2. Then just draw the graph 2, K, 2 and 2 and try to find out. So if there is a Hamiltonian or it's a bipartite. I said it's a bipartite. Okay, yeah, complete bipartite. Correct. Yeah. Complete bipartite. Just try to find out that Hamiltonian, is there any Hamiltonian circuit is there or not, and Eulian circuit is there or not.
So both of them are present.
Okay, then let's take 2 and 3. So then, right? Can you find a Eulerian and Hamiltonian graph here? Part here, yeah.
There won't be any Eulian path in K2.
What about Hamiltonian? Do you have Hamiltonian cycle here or any path or anything? You got it? How?
Like if you go from, can you label the vertices?
Yeah, sure.
The Hamiltonian path will be 3, 1, 4, 2, 5.
It will be 3, 1,
4, 2, 5.
4, 2, 5. Okay. Right.
Here you have an Eulerian as well because you have only 2 vertices of odd degree. So this is an exception. You have 2 vertices of odd degree.
Mm-hmm.
1 and 2. You have an Eulerian as well.
Yeah, you're right. Because
You will have a path but not a cycle.
no. If we recall the Eulian theorem, do you remember in the first?
Takes a path.
So okay, for in this case it is trivial. We will have a right. Okay, let me show you the theorem. Right? It doesn't. We can have Eulerian path because if we can't have more than 2 odd degree, right? So in that case it is true. But let's take more than a bigger network. What about this?
It's 4 vertices of odd degrees, so won't have either a path or
Oh. So then a tray 4 is here. There to T4, T4 to T4, 1 to 3. Okay, is correct? So here, can we have a, first let's talk about the Eulian. Can we have a Eulian here? No, why?
Because we have 4 vertices of odd digits.
Yeah, definitely from the Euler theorem we can say we don't have a Eulian. What about the Hamiltonian?
Yeah.
Hamiltonian, that we have to consider all nodes.
4, 1, 5, 2, 6, 3, 7.
What you have? What? 1?
4, 1, 4, 1, 5, 2.
So you said 1, 4.
No, you have to go from 4 to 1.
Okay, just a minute. So 4 to 1,
Then to 5.
1 to 5, and you said 5 to 3.
5 to 2. 5 to
Okay. Five to 2, 2 to 6, 6 to 3, 3 to 7. Okay. Okay, then connectivity. Connectivity, do you know the definition of connectivity?
If there is a path from one node to another, then that's it.
There should be some path from one to another node, right? And component means what? So we have some subgraph where, so it's actually maximally connected, so it is not totally connected. So there is no, for this example, this is a one subgraph, this is a one subgraph which are totally disconnected from each other, right? So strongly connected means what? So in case of directed, have this concept, strongly connected. What is this?
Means there is a directed path from every point to every other point.
Right. For this example, this is a one strongly connected component where from A to B there is a one path, again from B to A there is a one path, like that. For the nodes who are in A, B, C in that component, so for all of them we have some path. Similarly, in this example, can you give me a one strongly connected component? ABC again. EFG is again. EFG is not, I guess. No. This is not. Why?
Because we can't reach from
F to E, right? Again, is there any G to E? No. Correct. Okay, clustering coefficient. Do you know what is a clustering coefficient? No. So clustering coefficient is that, suppose a node I, so what is the probability of that node I, then his neighborhood is also connected. So what do you mean by neighborhood? So for this example, this is a star network, right? So neighborhood of I is what? All the nodes which are connected to I. For example, this is 1, 2, 3, 4. So its neighborhood is definitely 1, 2, 3, 4. Right? So let's take another example here. This kind of example, say. So label it. Okay. So what is the neighborhood for 7?
4, 8 and 6.
4, 8, 6. Correct. What about 3, 2 and 4? Those are neighborhood of 4, 3. Right? So now what is the clustering coefficient? Say for 3 is what? what is the probability that his neighborhood is also connected to each other? Yeah, definitely for 3 is 0. And for 7, its neighborhood is what? 4, 6 and 7. What is the probability that they are also connected among themselves? Is again 0. Right? So how we define mathematically? We define it this way. So in the denominator is what? Is the degree of that node into degree of that node minus 1. And what is EI? EI is actually a induced subgraph among the neighborhood of I. Right? So for example, say this. So clustering coefficient is half. So can you just try to use the formula? So Ci, it will be what? Its degree is 4. So denominator is 4 into 3 and its neighborhood is this 4 nodes. So now, so level it 1, 2, 3, 4. So what is the induced subgraph of 1, 2, 3, 4?
1, 4, 1, 2 and 2, 3.
1, 2, 1, 4, 2 and 3, correct? And is there any other link? This is the induced subgraph, right? So it will be 2 into 3. So it's half, correct? Correct? Okay. So is this concept clear or do you want me to, take another example and explain it? Okay. So I am giving away one. So can you find the clustering coefficient in general of, say in case of circle network? I am saying the circle network of with nodes n. N is any positive integer.
0.
Yeah, 0. So clustering for coefficient for any I, it will be 0, right? So as I say circle network, it will be like this. So let line network. So this kind of network, we can say this is a line. Again 0. So path, circle, line and say complete network. 1. For every I, it will be 1. Okay. Say star network. Say I is a central node. In case of central nodes, it's definitely 0. What about the other? What about the other? Because say this, if I label it as a 1, 2, 3, 4, in case of I, it's definitely 0. But for say, clustering coefficient of 1, can you use that? It will be 1 minus 0. So, okay, in case of it is undefined, right? Okay, degree distribution. What is the degree distribution? So, what is the probability of that? Suppose this is a one graph, this is another graph. So, now degree distribution is means, so we have a degree 1, 2 nodes have a degree 2 and then another node 2, it has a degree 3. Is it working? Okay, degree 3. So, now degree distribution is here, this given as a for 1, 0, it's definitely 0. For 1, it is 1/4, 2 is half, 3 is again 1/4. And for the circle, it's given that for 2, it's definitely 1 and 1 and 3, 4 is 0. So from here, can you interpret what is the meaning of degree distribution?
Probability of having a certain degree.
Yeah, correct. The probability that having a certain degree, and it is mathematically how we define it. N is the total number of nodes and Say for K is here what? 1, 2 and 3 and number of nodes that has a exactly, so for K equal to 1, it has a, there is exactly 1 node, it has a degree 1. For say K equal to 2, there is 2 nodes, say 2 and 4, they has exactly 2 nodes, right? Okay. Okay. So this is some special case in case of star graph, line graph and circle. That you can find out. Okay. Okay, what about the network diameter and average distance? Network diameter is the maximum path,
Maximum shortest path.
yeah, shortest path between any pair of nodes. Okay, let's take an example that. So this is a one network. So what's the diameter for this network?
5.
5 from this node to we can say n nodes like 7, 8, 9, 10. Okay. And average distance will be what?
Sum all the distance and divide by all the pairs.
Sum of the all distance between two nodes divided by,
Total pair of nodes.
it's the total pair of nodes. In case of say undirected, so say n is the number of nodes and it is actually what? N into n minus 1 by 2. What do you mean by that?
Total pairs.
What is this? It's actually total number of edges, right? Right. So in case of directed, it is 1 by n into n minus 1. Why? It's only one direction. But in case of undirected, it is actually, say for any distance from this to this is equal. That's why. Okay, these are actually for in the special case for what is the diameter in case of star and complete and line graph and cycle graph. Okay. Okay. So now weighted and probabilistic graph. So simply we can say weighted graph means, so there are some graph in the nodes they are associated with some weight. Or probabilistic means what? We can think about that there are some probability that link will going to form, right? Okay, somebody gave me one example of Google map. So do you think Google map is a what? Is a weighted graph?
The weights are the distances between.
Weights are distance, or we can say traffic, or based on that traffic or crowd or waiting time, based on that the maximum time or minimum time we will going to reach that destination. So I have one picture also, I can show you that. So suppose from this point to this point we have to reach, and so from the based on some traffic or thing we did distance, how we can calculate, or Google gives us the maximum or minimum time to reach that based on different roads, right? Okay, graph with weighted vertex. Earlier we have an example where the nodes or links have some weights. So now here there are some vertex who has a some weight. So can you think about some example here? Some real life example.
For example, let's say a robber wants to do a robbery, and
Okay, then
so he has a network of, let's say, houses, and in each house there is a certain amount of money that he can have.
and then okay, your notes will be that
The houses. And,
houses.
and if he can go from one house to another, then the edge between.
Okay, then you can put some weight on those notes based on some wealth or something like that. Okay, anything else you can think about?
University
I mean, you can say that the classroom size or the student capacity. Based on that, we can just assign some weights. Right, correct. Okay. Okay, cliqueness. Have you read about this definition, clique? It has some collected subgraph, and where it's a complete graph. So similarly, here it is a complete graphs with nodes 4. This is also a complete, right? And this is a complete. This is a complete. So it has some induced subgraph which are complete, right? Okay. So centrality measure, do you have any idea about centrality measure? Why we need this centrality measure? Have you heard about degree centrality, betweenness centrality and closeness centrality? Never? Okay. So centrality is a concept. So we try to identify the most central network or important networks. So in the degree centrality is very easy. So degree centrality means it is number of degree of each node. That's how we define the degree centrality. So how a node is connected. So in case of closeness and centrality, betweenness, so we have two definitions. So I will discuss about closeness and betweenness. So this is the mathematical definition of closeness centrality. So it is a summation, say I, J is actually what? Numbers of all nodes in a network Z, and the distance or shortest path from the network I to Z. It's a summation over all the nodes. Definitely I is not here. So V is the node of set of nodes. It's a summation over all nodes. Is the distance between shortest path or distance between from nodes I to J. Okay. So in case of, is this graph is visible to you, everyone? Okay, that given that the closeness centrality for A is 17 and closeness centrality for L, where is L, is 33. So can you just try to verify it? So let's for A. So closeness centrality for A.
You just have to sum up the length of the shortest path
From A to another, you have to consider all the nodes, right? So we have how many nodes? What is B here? The set of nodes. So it will be from A to L or M, right? It will be A, B, M, correct? This is the vertex. Now, this is the distance. So how to find the closeness centrality here? It will be, you have to consider distance between or shortest path between A to B, correct? What is the shortest path between A to B? It's 1, right? This is 1, right? Then shortest path between A to C. What is the shortest path between A to C? Again 1. This is correct. Then A to D, again it's 1. Then E, 1. This is how you have to calculate. So can you verify it? It is 17 or not? Just try to find both closeness and degree centrality for all these nodes. For degree centrality, it's easy. It's the total number of degree of each node. And now try to find what is the closeness centrality. So then we will have a comparison between four, 5 and 6. So for closeness centrality, just try to find 4, 5 and 6. Okay, definitely the degree centrality for 4 and 6 is more than 5 because 4 and 6 are more they have more links. But I want to see the closeness centrality for 5 and 4 and 6. Just count closeness centrality for 4 and 6 and 5. I think for 4 and 6 it will be same. See, closeness centrality for 4 and 6 it will be same, right? Because it's almost a isomorphic. The both side of 5 is isomorphic. So, but closeness centrality for 5 will be different definitely than 6, 4 and 6. And here it will be, say for degree centrality 4 and 6 it will stray and degree centrality is 5 is 2. Just count for one, I mean for either 4 or 6.
I think for 4 it's 20 and for 5 it's 16.
4 is
20.
20, are you sure? And 5 is 16.
17 for 4 and 16 for 5.
4 is what? 17? For 5? 16, are you sure? I think you know the closeness centrality for 5 should be more than 4 or 6. Yeah, it should be more.
Because it is in the middle, so to 4 and 6 it will have smaller distance.
What did you say? 4?
5 will have minimum compared to 4 and 6. Because it is in the center.
Okay, that what in case of this? So what about this in case of this? So when you calculate, so note this is a closeness centrality, right? So T5 is, it is normalized. It's a normalized one. Now here you can see the closeness centrality for T5 and for 4 is greater, 0.6 and 0.55. So just try to calculate it properly again. Just try to find the closeness centrality for 4 or 3 or 5, anything, and then you will see that the closeness centrality for 4 is more than these two nodes, though they have a more connection, right? So that thing, what is the interpretation in this case? Why the closest centrality is more? Is because that see the 4 is the crucial network, crucial node. If we remove it, and what will happen? Then we will have a two complete component. It will be a two disconnected graph, right?
There is summing over all the distances, right? all other edges, right? So all of the vertices. Yeah, then the middle one is 10 and the side ones are 11.
Middle one is 10, side one is 11.
Yeah.
Now, what is the normalization equation?
Normalization should be some divided by total sum.
But then it will be A of
Total. Okay, then I'll calculate and we'll discuss this later. Okay, time is running out, so let me just finish this. Another one, so betweenness centrality. So I'll calculate and let you know in the next class tomorrow. Okay, the closeness centrality part. So for the betweenness centrality is how we do that. So betweenness centrality is what? Is the total part from each node. You have to consider the V is the set of all nodes, right? So you have to consider all the total shortest path from each node, each pair of nodes, and all the total paths of each pair of nodes via that point or go through the point I. Okay. So suppose this is one graph, right? So if we have to calculate betweenness centrality for this point, nodes say 1, 2, 3, 4, 5, 6, 7, right? To find this betweenness centrality, what we have to consider? The betweenness centrality for T, it will be, you have to consider all the path so 1, all pairs you have to consider. So 1 and 2, is there any path where that is 3? No. 1, 4 definitely one path. 1, 5 definitely one path. 1, 6 and 1, 7. Okay. So then it will be total path from, or you have to consider all pairs. Okay. This is how you have to calculate. So again, so here it is calculated and we see that the betweenness centrality for 2 and 4 is 8 and the betweenness centrality for 3 is 9. That means the betweenness centrality 4 is more than 2 and 4. As I said earlier, the 3 is more crucial nodes for this network, though it has a less nodes, degree centrality is less. Okay. Okay, so similarly we have a more centrality nodes, so based on some prestige and eigenvalue. Do you know, did you have linear algebra course? All of you had? Okay. So for each graph, we can have a matrix. So how we define the matrix? If there is a one link, then we will say the entity will be 1. If there is no link, it will be 0. So this is how we can draw a matrix. So for these networks, so for undirected one, definitely. So for, say this is 1, we have a 4 nodes, 1, 2, 3, 4 and it is 1, 2, 3, 4. So all diagonal entities will be 0 because it's a simple graph, we don't have loop. If there is any loop, then it will be 1. So from 1 to 2, is there any link? So it's 1. From 1 to 3, there is no link, so it's 0, right? So in case of directed, we will consider a direction, right? Okay. So this is the adjacency matrix for these two graphs. So similarly, this is another example of adjacency matrix. This is a bigger example. Okay. And this is how it look like a connected component. For this component, we will have this adjacency matrix. For the component with red node, we have this adjacency matrix, right? Others, all these entries are 0. Okay. Okay. So I was to say that I am going to talk about link formation, how the links is formed. So suppose I have a network Z. Okay. So this is a one network. So now my question is to find a efficient network. What do you mean by efficient? Suppose this network is generating some word. They are forming some link. So in return, there are some, say they are forming some word or anything. So in return, so they form some link, means say I, J are in a link. In return, they are in that network. So in return, they are expecting something. So I will discuss about detail more. Just I am going to give you some hints. Okay. So now I have to find. So there is a function V. So this is a one network. So there is a one function V that is defined on the complete network. Say G to the N. So or V is the vertex set. Right, is a real function. So only the criteria is that V of empty will be 0. Empty means empty network with isolated node, there is no edges, 0. So now, so we have to find, say, we know that all, if the complete network might not be efficient. So that V, we have to find the graph Z or Z prime is a subset of Z and any subgraph such that the word or this function of this is greater than any G or yeah.
Ma'am, just to clarify the notation, what is GV?
What is GV?
G raised to V.
Oh, this one, this is subset.
No. V is a function from G raised to V to reals.
This is domain, okay, the complete network. Suppose B is the node, set of nodes, that will be the complete network. Okay, ZB is the complete network. So in case of it, what will have the complete network? So in case of it will be difficult to draw, but still. So we have a very dense network here, right, like this. So we'll have more edges. So suppose this is my ZV, and now the question is that there is a one function associated with this GV such that this condition is always hold, and so suppose this function V is not like that suppose I and J, they are sharing a link, but that link might not be generating that much. So we have to find a subnetwork of ZV, sorry, this is a ZV, a subnetwork such that the word or that function is more than any other subnetwork. So this is, we call it efficient network. So this is a mathematical definition I am just giving you, but you know, when I am going to talk about more, it will be clear to you. So to find this network G prime, so the question is that, say, suppose the whole network is connected. Now under the what circumstance or situation, the one link I will wants to delete the link edges with another networks. So this is my whole complete network, right? Now to find a subnetwork of G prime, either I have to create or delete, mostly I have to delete some nodes, right? And then I am going to find a subset of GV. So the whole complete network might not be that efficient. Sometimes this subgraph will be more efficient. They will generate more, right? So I'll give you more real life example, then it will be more clear. So then what are the conditions then we have to find that efficient network? So we'll talk about more to how to form that strategic formation of nodes. So find this is called efficiency, and pairwise deleting or adding nodes is called stability. Okay, we'll talk about that. So to know this, so I divided my lecture in this part. First we have to know a little bit idea of cooperative game, TU cooperative game, and then communication situation. After that we'll talk about network games. So parallelly we'll talk about some solutions also, and lastly we'll talk about stability versus efficiency, the network formations. So then in this part, we have some allocation rule for network games, say like Bayesian positions, equal division, a lot more. Then we'll talk about the stability and efficiency of all these allocation rule. Okay, so before that, you have to know a little bit, not know that much, linear algebra. So what is a linear space, dimension and basis? Okay, so because this the setup of cooperative game is a linear space, so just try to collect it, linear space, dimension of its linear space and basis. These three things, more than that. Okay. Then we'll talk about, we'll start from TU cooperative game tomorrow.